Thank you. Hello, everyone. I suppose you can hear me well. Today I'm going to talk, as usually, about membrane and WebRTC. So I'd like to start with asking you, who have you ever used membrane? Anyone? One? Okay. Not so many. That's great because this will be a quite introductory presentation. And whoever did something with WebRTC? A bit more of you. Okay. So let me start with introducing WebRTC itself anyway to you, and then I will progress to dealing with WebRTC in Elixir with membrane. So I will talk about architecture and usage and the goals for our framework. So WebRTC is an open source standard for video conferencing that consists of state-of-the-art technologies. So it doesn't reinvent media streaming. It rather puts together what is already done, what was already done even years before WebRTC existed, and it standardized the stuff so that we can all use the best technologies. Also, WebRTC brought video conferencing to browsers because before, to have video conferencing in browsers, you would need to install some weird extensions, Java applets, and nightmare technologies. So I think it's no exaggeration to say that WebRTC brought video conferencing to browsers, and it's still the only reasonable way to stream a video from a browser. So whoever streams a video from a browser, so has any video conference in browser, uses WebRTC basically. And WebRTC was also meant to be a peer-to-peer standard, so you can connect two browsers together without any relying server, or even more browsers, but in peer-to-peer manner. It will be a mesh, of course. So let's say we have these two browsers and we want to connect them together, establish a video conference between them. What do we need is a server, but it's not a media server, it's an HTTP regular server that will allow us firstly to give the HTML web page that we can use to embed our video conference. It will help us exchange SDP messages that are used to describe what are we going to stream, what kind of media, what kind of codecs, how much streams both peers are able to receive. And finally, the interactivity, connectivity establishment messages are also transferred to this signaling server. This is needed basically to overcome NAT to connect together, establish a direct connection between the browsers. Quick note about the SDP. This is an SDP message. It was meant to be like human readable, but also easily parsable by a machine, and it turned out to be neither. So, yep. As you can see, it looks flat, but this is how it looks after parsing. We created XSDP library to handle SDP in Elixir, so it's actually a nested struct. I also heard that when Mozilla implemented the SDP exchange mechanism in their browser, they made like a hackathon and they closed themselves for a week and tried to implement this. And I don't know what they did there, but now each SDP from Firefox contains this. Let's get back to our session and video conference. So we have this connection between two browsers, direct connection, yeah. And then we want to exchange some media there. So what we will use is SRTP over UDP. SRTP stands for Secure Real-Time Transport Protocol, and it's a transport protocol directly aligned for transmitting media. So we don't want to use TCP and all its mechanisms because SRTP already does it in the way that is mostly suitable for media. We will use UDP whenever possible. Sometimes it's not possible, but whenever possible, we are going to use UDP. And in these SRTP packets, we're going to send encoded media, so opus for audio, and VP9 or 8, or H.264 or 5 for video. Usually, VP8 is used. But if you want to connect another browser to this our video conference, then we need another two connections because it's a peer-to-peer protocol. And if we want to add another browser, there are 6 connections and 10 connections for 5 browsers. You can see it doesn't really scale even for like small video conference, and that's really a problem because we need to do a hack to use WebRTC, which is a standard technology for video conferencing, to have any video conference that is greater than 4 or 5 peers. And the hack is to have a server that will relay the stream to accept the stream from each browser and relay it to all other browsers. And this is called SFU, so Selective Forwarding Unit. And the other approach we can use is MCU, so Multiconferencing Unit. It will accept the stream from each browser, mix together all the streams, and send one mixed stream to all peers. So that's the other approach. And basically, to create that server, we'll have to make it act as a peer in a peer-to-peer conference, because WebRTC works peer-to-peer. So it has to exchange the track information via SDP, establish connection via ICE, even though it doesn't make really sense because it's a server. We don't have an NAT to overcome, usually at least. And it has to exchange encryption keys via DTLS. That keys are required to encrypt the stream via SRTP. This is also a problem because each peer has its own set of DTLS and SRTP keys. So you have to decode, decrypt, and then encrypt the stream for each peer, and that is really CPU-intensive task. Also, when we decrypt that stream and demax it, because we have possibly a lot of audio tracks in one RTP streams, or audio and video tracks in RTP stream, then we take the tracks out of the RTP stream. And in case of SFU, we have to do all the way around. So we have already the SDP exchanged, ICE established, but we have to encrypt the stream back and max it. Max it and then encrypt it to send to other peer. In case of MCU, we have more steps because we have to decode the stream, so decode the media, then mix them together and then encode them back. And this is really CPU-intensive task. That's why most of available WebRTC servers go for SFU approach. But in case you have like a lot of streams and they are usually not really high-quality streams because no one is able to handle such many streams with high quality, the browser, then it's maybe better approach to mix the streams together and avoid the overhead of sending each stream separately. Okay, so now let me proceed to the membrane part. So membrane is basically about making pipelines. Here we have a pipeline. 4 elements, source to filters and async, and source gets the media from some place or generates it, then sends to the filter, to another filter, and to the sync. That's the pipeline, and that's the abstraction layer that membrane delivers. So let me try to show you how to construct, or how does it look if we create a pipeline for a WebRTC server. Let me start telemetry stuff that we have in membrane. I really hope it will work. I tried it 3 times on the presentations, and it's going to be first time it works, I hope. So keep your thumbs crossed. OK, so here I started the timescale database that is responsible for collecting metrics. Here I started the membrane dashboard. This is a tool that uses these metrics to visualize what's happening inside the membrane pipeline. And now I'm going to start a video room demo that's available on membrane GitHub. That is a simple implementation of a use case of our WebRTC engine. So now let me go to the dashboard. It's here. I have to drink something, sorry. And I'm going to do a start live update so that when we start to use our server, we'll see something here. So in another tab, let me open a room. Yep, another me. And this should populate in a moment. Yep, it does. Here, for example, we have buffers per second. So it's around 80 buffers per second sent and received by some element in our pipeline. I'm not sure which, but potentially we can improve this API, I mean UI, to be more friendly. But what I'm going to focus on is this. This is actually the pipeline for a single peer in WebRTC server. So looks quite complicated. So let me get back to a presentation for a second. We have a concept in Membrane that's called beans. If you want to hide a complexity from user or hide some logic that exists within a pipeline, you can wrap some elements into bean. And then if you create a proper API for that, you can, buttons don't work. Then you can have like bean that is visible from user's perspective, just like a single element, but it encapsulates more logic. So what I'm going to do now is to collapse a bean. Oh, I have to enter some snapshot mode. Okay, feed view. So again. Here we have an endpoint bin that is responsible for receiving and sending, in this case, only receiving the tracks from user, and two T elements that are taking the stream from the endpoint. This will be for audio, and for the other one will be for video, probably. And they are able to provide the stream to some other peer. So let's add some other peer. Even more of myself. So yeah, I have to exit the snapshot mode. Whoa. Oh, yeah, it doesn't even fit in a screen. So I'm going to get back here and collapse some stuff. Yeah, if someone knows a library that does the relayouting of such graphs in a better way, I would really appreciate. So here we have two endpoint bins, and they exchange the tracks, the streams. And so the first bin sends to T elements, as I mentioned before, and the T elements can provide the other endpoint bin with the streams from the previous endpoint bin, and then the other way around. So that's basically how it works. If we wanted to have more bins, so more peers, it would be connected. They would be connected to these T elements as well. So now let me show you what's inside the endpoint bin to get a little bit into detail. And and this I'm not going to figure out how to read out, so I made my homework and did it before the presentation. So here we have from the left ice bin, so the stuff that is responsible for establishing the ice connection and gathering the streams. Then this ice bin forwards the stream to RTP bin that is responsible for handling all the RTP stuff, so decryption and demaxing. And then to these orange boxes that are API of the endpoint bin, and then to these T elements. And the other way around, we have the also endpoint bin pads, these orange boxes that take the stream, put it through a parser. For example, here we have H.264 parser that is needed when we deal with H.264 stream. Then the stream goes to RTP bin. The RTP bin also outputs each track separately, so we have to mux that together with the ice funnel element, and then it comes to the ice bin. That's basically how it works. Why actually I'm talking about this, and why this is, I think, this is a flexible approach to having multimedia streaming. Again, one endpoint sending a stream through a T to another endpoint. So if we wanted to dump this stream to a file, then it's as easy as plugging part of a pipeline that is responsible for dumping to a file. And from architectural point of view, it's simple as that. Probably it would be even exactly that, so we can plug membrane file element, and then the stream will be dumped to the file. If we want to do some preprocessing, you can do this as well. Even more, if you want to deliver the stream to a wider public and you don't want to waste all your resources, but you can sacrifice some latency, there is a protocol for that called HLS. And this can make use of regular CDNs to deliver the media through HTTP to wider public. So Membrane has support for HLS, so it's about plugging the HLS just as the file was plugged and publishing the stream. Even more, if we want to have some custom functionality that is not implemented in Membrane, some custom filtering, it can be also plugged within the pipeline. So we have here a custom filter. It's creating a filter is a matter of implementing a behavior that is delivered by Membrane. Then we can do anything with the stream what we want, and then proceed, send it further to the other part of the pipeline. What is given by the Erlang virtual machine is a fault tolerance, as we well know. So since the rooms are actually processes, then when a room fails, all the other rooms within the video room, within our video room, can run without being affected in any way. But what is even more important, when we have this file pipeline and the file fails, we can still deliver the stream to the endpoint bin because Membrane has quite some mechanism of supervision built in itself. Buttons don't work. Oh, and finally, the Membrane dashboard that I showed you just before. It's capable of displaying any kind of pipeline, so no matter of modifications that are applied to the pipeline, we can look them up with this dashboard, and any like feature that is implemented for pipelines as a generic abstraction can be used in all its implementations. So a few words about how to use that in practice. So basically, the Membrane RTC stuff is split into Membrane RTC engine that serves as a backend, and Membrane WebRTC TypeScript class that can be used on the front end. And all information that they exchange, apart from the media itself, comes through user code, so user application backend and user application frontend. That's why Membrane WebRTC engine doesn't impose any kind of transport of API to someone's system. It can be just integrated into what already is used, or user can choose whatever fits him the best. For example, it can be a live view application, it can use Phoenix channels, but it can use also a GraphQL for transport. It doesn't matter. But to make the user not aware of, to not force the user to be aware of all the communication that exists between a Membrane RTC engine and the frontend, we introduced something like Membrane media events that are that user is forced to pass to the other part of the system, but doesn't have to understand them in any way, so that we can hide some complexity, as for example SDP exchange or ICE exchange from the user. And this is all split into two packages. First is Membrane WebRTC plugin that has the endpoint bin inside that I already mentioned. And the other is Membrane RTC engine that puts together these endpoint bins and links them together. So, and it also has the front-end part I mentioned. And we have a demo on GitHub that uses RTC engine to set up a simple video room service that I just showed you. So what are we doing now is improving performance. We have some aspects now that we are dealing with. So for example, filtering tracks that are not used, for example, a silent audio that is coming from user. Reducing overhead of flow control. We have a flow control mechanism that is similar to GenStage, so it's based on demands. And we so that it adds quite a lot of overhead. So we are working now on reducing that, and also reducing message passing, as you saw already that we receive tens of buffers per second. So sending them all as separate messages is quite CPU intensive. We also work on distribution room over an Erlang cluster. Actually, we already have that, so that because it's just about spawning the processes on a separate node, so this is a power of Erlang. But we are still working on adjusting our architecture so that fewer messages were sent between nodes. And finally, our goals. Of course, we have a lot of goals. For example, scaling more to have like bigger rooms, or having more features and functionality, and be more stable. That's all obvious. But the general goal for Membrane is to make media streaming simple and flexible, so that, for example, now when you want to do an web service, you just type mix Phoenix new, and it goes. It wasn't like that some years ago. There were times when you had to like create SQL instructions manually, SQL commands, or you had to adjust CSS to fit multiple different browsers. And in the case of media, it's now. So the WebRTC implementations in browsers are different. The backends are hard to deal with, so that's what we are going to change. And I think it's already started, so it's already quite simple to set up Membrane video room, despite it's in alpha and it's very early stage. So I'd like to thank you for all my team that works hard to develop Membrane WebRTC, and I would thank you to all external contributors who really helped us recently, both with coding and designing. I'd like to thank Software Mansion for being behind Membrane since its beginning, and thank you for being here with me. It's a pleasure to meet you in person. Thanks.
Thank you. Do we have any questions?
Hi, so I've been tracking your progress on Membrane for quite some time on WebRTC, because we had a possible application for it. I see it's in it made good progress, so congratulations. You really make big advancement in this field. When do you think you'll be out of alpha, like ready for production use in some serious applications?
Well, it's hard to say. I think we're having like some use cases of membrane and including membrane WebRTC that we are trying hard to put into production, and we'll be really happy if we could do this by the end of the year. But this field is quite complicated, and we started from scratch, so it's really hard to predict how the things go. But the demo I showed you already works, so it's a matter of rather becoming more stable than writing things from scratch again.
Thank you.
Thanks.
I have a question. So you showed video conferencing, and I was wondering if we can use Membrane also for video streaming, like movies or something like that, or audio.
Yep, sure. The assumption behind Membrane is to be flexible and to allow to compose your own pipelines designed, aligned to your use case perfectly. So for sure, Membrane started as a framework for streaming radio stations. So it's also, actually there are radio stations working on Membrane now. So it's like very versatile stuff. You can compose different things out of it. Definitely it's possible.